Okay, all right. So I have a couple of, well, let's see. Thanks to everybody for showing up for the meeting today. Today I've got a couple of status updates to discuss and a couple of points or a couple of status updates to go over and a couple of points for discussion. And then I think the folks at Missing Link Electronics have a couple of points for discussion as well. So I have a bunch of slides, but I'm probably just going to skip over a bunch of stuff unless people want to go into more detail. All right. So the agenda I have for today is first some status updates, and then I'm going to perhaps talk a little bit about the descriptor format and the shared interface data path, depending on. I've talked about these before recently, but I know there's a couple people that have had some questions about these, so we can take those and pull up some of those slides as necessary. All right, so moving into the status portion of this. Over the past couple of weeks, I've been hammering on getting Corundum operational on Stratix 10 devices. Specifically, we need to run on the Stratix 10 MX as part of the research that we're doing at UCSD. And then the folks at the MLE need it running on the Stratix 10 GX for a product that they're working on. Both of these use the H tile or the L tile, depending on which part variant you order. So what I've been doing is getting that operational in the simulation framework, and then getting Corundum running on there. So talk a little bit more about that in a minute. I've also been working on some address-based abstraction components. This is kind of a modification to the CocoaTB extensions for AXI and for PCIe. The idea being that with this abstraction, it doesn't matter if you're using AXI or PCIe or whatever, the interface that you can use from the simulation framework is going to be the same. So the point behind this is to be able to simulate Corundum running on like a Zinc device, in addition to PCIe. And then I also want to discuss variable length descriptor support and the shared interface data path components that I'm going to be working on next, basically. And then a couple of longer term things, including the PHY CSRs, the 10G25G switching, and some address-based reorganization. All right. So moving on to the Stratix 10 H-tile L-tile support. For various reasons, we need to run on Stratix 10. As of last meeting, I had the Ethernet interfaces running at 10G. I made some progress on getting stuff running at 25G, but I'm going to table that for the time being. And 100G is, same kind of thing, tabling that for the time being. For PCIe, I got the shim working at Gen 3 by 8, Gen 3 by 16. I need to do a little bit more work. Got to get my head wrapped around exactly how to deal with the segmented interface going into the PCI Express IP core for the highest possible performance. That's more like on the transmit side, you can get away without really dealing with it, but on the receive side, I mean, it comes out segmented, so you have to destripe it one way or another. I got the DMA benchmarking design running on both the Stratix 10 MX dev kit and the 520N MX board from Bitware. And then I also got Corundum running on the Stratix 10 MX dev kit at 10 gigabits per second close timing. It worked. So that's excellent. That's the first, non-Xilinx board that Corundum has run on. But unfortunately, it does not close timing on the Stratix 10 MX on the 520N MX board. And the reason for that is the parts are different speed grades. We're running into a bunch of issues with the queue management logic. I think the TNS was about minus 100 nanoseconds or so, which is not great, but each of the failures was, I think the worst failure was about 200 picoseconds or something like that, 0.2 nanoseconds. So lots of little paths all over the place that are failing. So yeah, something needs to be, we need to do some optimization from a timing perspective to make it work. But the problem is that the parts that are failing are related to the queue management. That's all going to be ripped out and replaced when implementing variable length descriptors. So I don't want to waste time on optimizing this stuff if it's just going to get ripped out. So continuing to work on this and implementing Gen 3 by 16 and whatnot, this is now all blocked on variable length descriptor support because I want to implement that, and then we'll hammer on the new modules to get those to close timing. because those are going to be, more powerful and more flexible and whatnot. There's also some ancillary stuff like flash access and I2C and whatnot. That's all going to be to do for now on these boards, but the core data path at least is working. So now we just need to do some cleanup work. All right, so that's pretty good. The next thing that I have been working on over the past couple of weeks is the address-based abstraction components. The idea is this is some functionality that's going to be added to CocoaTBX AXI that can then be used by CocoaTBX PCIe and potentially other components as well. This supersedes kind of this simple region handling components that I'd implemented in CocoaTBX PCIe. The idea is you can emulate, a system on chip style address space that has a bunch of different, components sitting in it at various addresses, including, a region for, DRAM and then regions for interfacing with various peripherals. And this, potentially can include PCIe devices as well. And if you're using the same abstraction for everything, then it doesn't matter if you're using AXI models or PCIe models. The driver components, the test bench components are going to be interfacing with the same API, basically. So the status for this is actually mostly done at this point. It's taken a while because, putting together this kind of an abstraction, you want to make sure that's going to work. So I kind of put the abstraction together, and then I have to modify CocoaTBX AXI and CocoaTBX PCIe to use it, and then I have to modify the test benches for, Corundum and whatnot to use this abstraction as well. And once I get everything kind of running, then I can see, okay, well, I got to fix this, I got to fix that, and make some adjustments to the abstraction. So once everything's all sorted out, then I'm going to go ahead, early this week, get everything all pushed up to the various repositories and make new releases for CocoaTBX PCIe and CocoaTBX to AXI. But yeah, so last night I got the driver model for Corundum, the PCIe version, running with this new abstraction layer. And I got the AXI version all the way through the initialization phase, but there's a problem with the DMA side of things that I got to sort out in the model. So that's pretty good progress. So yeah, expect this, live relatively soon, and hopefully we'll be able to take this and work out whatever bug the MLE guys were having when they were trying to run the AXI version of Corundum on Zinc MPSoC. It's always easier to debug this kind of stuff in simulation than it is to debug it in hardware. All right. And just for a real brief overview of, what I've put together for this abstraction so far, it consists of a bunch of different objects. Kind of the core object that everything else extends from is something called memory interface. And this one, it basically gives you an abstract read and write method that you have to, implement based on what object you're implementing. And then it provides word access wrappers, so all the read write words or D words or whatever. And it also allows you to create memory windows. So memory window it also extends memory interface, and it basically is a view onto a portion of the address space. So with memory windows, instead of passing around, integers in Python or whatever, you can just pass around memory windows. Because if you have just an integer and address, well, what do you do with that address? You also need some object reference to actually perform a read or write. With the memory window, well, you can just call .read or .write, and then it does the rest. All right, so everything implements memory interface. Next object is region, which extends memory interface. So the idea with region is that it implements a portion of an address space. It's like, for a peripheral, it's going to sit in a particular region. For for PCI Express, you might have a region that, is connected to the PCI Express bus. And if you make any read or write operations on that region, that'll be translated into PCIe TLPs that go out over the bus. And then we have address space. This is an extension of region. And the address space allows you to register regions for various sections of address space. And this can optionally do address translation. So what you could do is register a memory basically somewhere in the address space, and then it will translate. So if you make an access inside of that region, if you access the base address of that region, then it'll get translated to an access to address 0 on that region. Or you can turn it off and it is transparent. So this is used for like PCI Express when you have a section of address space that you just want to translate into TLPs over the bus, but you just want to keep the addresses the same. But you don't want to start from address 0. You want to start, somewhere down the line. So in that case, you can set up, you can register it in a transparent way such that it doesn't actually subtract off the offset, and it just passes the addresses through directly. And then finally, we have a pool. This one extends address-based, and this one implements a very simple buddy allocator algorithm that allows you to allocate little pieces of backing memory, basically. So you can use this for, DMA kind of stuff. You can use a pool to allocate a DMA buffer, and then over AXI or PCIe or whatever, you can read or write stuff into that buffer. And then you have direct access to, that little piece of memory to either read what's there or, write something there that you can then access over DMA. And the way I'm setting all the stuff up is this will be usable from, both PCI Express, sort of as it works now, but also with various AXI components. So you can attach AXI masters, AXI slaves, things like that, as well as the PCI Express components, and test everything together. All right, so that's the address-based abstraction. The next thing that's on the chopping block now, because of the timing closure issues with the 520 and MX, is the variable length descriptor support. So the idea here is that we need to overhaul a couple of modules in the design to support some slightly more complicated descriptor parsing operations. So the idea is the current queue management logic doesn't handle variable length descriptors. It's designed for all the descriptors to have fixed lengths, and you can just request a descriptor and it'll give you the physical address, and then you can just DMA it. That doesn't work if the lengths of the descriptors are variable, because you need to read one descriptor before you can know where the next one starts. So what we need to do is have a simplified queue manager that doesn't have any of this additional logic. It basically just stores all of the state, and then we'll have a much more kind of comprehensive descriptor fetch and header parsing module that can read descriptors in blocks and parse the length and type information from the first couple of bytes of the descriptor, and then hand them off to the logic. And this is potentially where we can include things like support for LSO, where you have multiple packets that are being generated from a single descriptor. The way the rest of the data path works, it expects one packet per descriptor. If we could make some small modifications to the descriptor management logic, what we can do is generate multiple copies of an LSO descriptor. Basically, each one of those will then be converted into one packet from that, or one piece of the original large segment. All right, so for this, I'm basically just starting working on this. So a lot of work that needs to be done to make all of this work, but since we kind of have the descriptor format more or less sorted out, this hopefully won't be that much of a stretch to get everything operational. All right, and then finally we have the shared interface data path that I'm going to be working on over the next few weeks as well. So this one, the idea is to take all the data path components that are in the port and pull them back into the interface. So each port will have only the transmit scheduler and FIFOs, the only things that every port needs to have. And then all the other components will live in the interface. We'll have a single path for RX and a single path for TX to ease implementation. So in the application section, doesn't matter what port you're sending traffic to or receiving traffic from, it's all going to be on one streaming interface. And this will also support things like traffic classes for prioritization. So if you want to implement PFC, that's going to be a necessary component of that. And I'm also going to have to implement some sort of credit-based flow control to alleviate headline blocking. This is important on the transmit path because we've got this, high-speed data path that then splits off into multiple lower speed ports. So if one of the FIFO stacks up leading to one of the ports, then that'll cause the whole data path to get all jammed up. So we need to make sure that nothing is ever going to be sent into the data path if there isn't FIFO space on the other end to store the result. before it makes its way onto the wire. And as part of this, I need to build these shared memory FIFOs that are going to connect the ports to the core interface data path. And I have kind of an initial version of that in the AXI stream switch module, but there are some issues with that. So I need to make basically simplified versions of it that are, one-to-many and many-to-one instead of the AXI stream switch, which can do many-to-many, and as a result has some somewhat problematic design trade-offs. So that's what I'm going to be working on over the next few days after I get the changes to the simulation framework squared away. All right, so that's the core of what I wanted to discuss in terms of status updates. I have some slides on variable length descriptors and let's see, and the shared interface data path to go into some more detail if people have questions about that and want to talk about that in a little bit more detail. Let's see, I think Xiang Rui was asking about that. I don't know if we want to discuss that now or if we want to turn it over to the folks at MLE who I think had a few ideas as well about stuff to implement. So
yeah, we could talk about it right now. That's
okay.
fine for me.
All right. So you want to talk about the shared interface data path and what we're going to do there?
Yeah, right. We can do it right now because we have a prototype that we will need to have a data path components like this. So maybe we can talk about
okay.
it right now.
Well, so let's start with what yeah, let me just go pull up. I have a little block diagram here that discusses the data path in a little bit more detail. So I showed these same slides in a presentation, well, a couple of weeks ago. Anyway, we have the this is kind of what the block diagram currently looks like of Corundum, and this is the way it's currently set up. And with the shared interface data path, we're going to pull these components that don't really need to be dedicated to each port into the interface, and then each port will have just the transmit scheduler FIFO, and then whatever interface logic is required, the max or whatever. So what exactly do you need for the prototype that you guys are working on? You said it sounded like you wanted to kind of throw everything into a single data path of the transmit and receive, right?
Yeah, right. So in our prototype, we want the packet that we send into the FPGA to be sent back to the software. It's a kind of like a virtual switch offloading thing. So, but we need high performance for that.
Okay, so you're talking about turning packets back around to the host?
Yes, right.
I see. Okay, so you need high performance. So you're talking mainly about latency or throughput or both, or?
I think both. We have implemented a DPDK, a type of driver on the top of Corundum, but we need high performance on this
like a DPDK side. PMD or just kind of DPDK style?
It's a DPDK style.
Okay. Exactly. So just kind of a user space driver.
Yes, exactly. So I think we'll need a high performance in regard of both throughput and the latency. So, but we do not care too much about the performance between different ports because this is a NIC. I think we don't need to deliver high performance between different ports.
Right. So you're trying to offload switching more, from the standpoint of the host. So if you have like virtual machines or something running on the host and interconnecting those.
Yeah. If you remember it, we have implemented a RMT pipeline based on Corundum. So we want to make that RMT pipeline work for virtual interfaces.
Gotcha. Okay, I see. Well, so does that mean you also need something like a SRIOV support in Corundum, or is your user space networking stack going to be good enough to, well, I guess if you don't do SRIOV support, then you're just talking about, multiple net devices on the same host,
Yeah,
not
yeah,
using PCIe pass through.
yeah, that's right.
Well, I mean, with the way things are currently set up, you could certainly turn packets back around if you wanted to. The application section has access to both the TX path and the RX path. So the issue with combining both the RX and the TX path into a single interface is then you run into head of line blocking issues that are a little bit more difficult to solve, because it's not too hard to apply back pressure against the transmit schedulers, but you can't really apply back pressure against the receive max.
Yeah, I see. So yeah, I realize the problem with the performance bottleneck, but I'm not sure. I can do it on my own, but I'm not sure how to solve the performance issue, if there's a better way to solve it.
Right. Yeah. I mean, to some extent, I don't have a complete handle on the problem either. I think it'll become a lot more clear once I start putting some of the pieces for this shared data path together and see what the performance is looking like. I think in the transmit direction, it's not going to be too bad because I can just do some sort of a credit-based flow control scheme, and that's pretty much guaranteed to work correctly. In the receive direction, it's a slightly different story. But since everything is just feeding into the same, data path feeding the host over PCIe, it's less of an issue. You don't really have issues with head of line blocking in that direction. If you run into bandwidth related issues, I mean, you're going to be dropping packets no matter what. So, but yeah, I guess what you guys could always do in your case is combine the RX and TX paths in the application section, multiplex them together, and then feed your data path from there. And then I guess we can potentially just iterate off of that and see what the performance looks like. And then, because that's the nice thing about the application section, you can implement whatever logic that you want in there, and see how it works. And then if something is compelling enough to implement in pull out of the application section and implement in the core of Corundum, then we can do that, if that makes sense.
I see it. I'm not very familiar with the application section because I haven't followed Corundum for quite a time. Is application section provides such a kind of a arbiter that merges all the data path of different RX together into one pipeline, or is it just one section for one data path?
So the way it's going to work with the shared interface data path is the streaming interfaces closest to the kind of core PCIe data path are going to be combined into one across all the ports. The application section is one section across everything. It's not a per port thing. Let me see. Do I have just the application section I can pull up right now? I had a very, very high level overview slide that just kind of listed out what the interfaces are, but what I can do is just show what the interface looks like in the actual Verilog here. Where is that file? Just to give you an idea what it's capable of. So kind of the idea with the application section is you can get access to a bunch of different components inside of Corundum. And from that, you can implement customized logic to do whatever you want, basically. All right, there we go. Okay. All right, so hopefully you guys can read this. The text might be a little small, but this is the template application module that I have put together. This one is in the repository right now that you can take a look at. So this provides, there's an AXI Lite interface. This one is dedicated to the application section. This one will appear as PCI Express bar number 2. The default NIC bar is bar 0. So bar 2, this is dedicated to the application logic. And there's a config.tcl. You can program in exactly how much address space you want dedicated to the application. So this shows up as bar 2. Then there's a master interface here. This one has visibility onto the standard NIC control register space. So if you need to change a setting or read something, you can do that here. And then there is a DMA interface. So it has the descriptor connections here and the segmented RAM for control and for data. So with this, you can access the host address space and read and write whatever you want. There's a PTP clock connection, and then there's a whole bunch of Ethernet related connections here. So this first one, this is the lowest latency connection. This one sits basically right at the Mac. So if you want to inject some really low latency control frames or something like that, if you want to implement PFC, for example, you can sit on this interface and you can do that. So this one runs synchronous to whatever the Mac clocks are. So lots of clocks associated with that one. This one here is the synchronous Mac interface. So this one is exactly the same as the previous one, but there's a shallow clock crossing FIFO in between the two. So this one, same idea, but slightly higher latency. And then this one is the internal interface that sits closest to the internal data path logic. And this one, right now it's per port, but eventually this is going to be reworked to have one streaming interface per interface module. And with this one, you can take the RX and TX and do whatever you want. Yeah. So if you're looking at the way this is set up here, we have, so we have, let's see, S is, right, this is the input side here for TX, and then the output for TX, and input for RX, output for RX. So with these components, you can put whatever logic you want in the TX path and in the RX path. And if you wanted to take the TX and RX traffic, from both the core data path logic and from the ports and merge it all together, and then do something with that in the application section, you can do that. So this module here is kind of the template application block. So you can make a copy of this and then add whatever logic you want down here. This one is just looping everything back. But yeah, you can implement your own logic here to cross connect this stuff however you want, and implement the functionality that you want that way.
Yeah, I see. That's very helpful. So do you mean that I could potentially add a arbiter in the front of the pipeline to merge all the input together and add the RMT there? And
yeah, if that's what you want to do for your application, then yeah, you'd be able to do that. And then we can at least evaluate, what that looks like from a performance standpoint and a flexibility standpoint and resource consumption and whatnot. And if it all sounds reasonable, then, maybe some of this stuff could be considered for, the core Corundum data path, because you're probably not the only one that would like to be able to do, software switching type stuff. But, the flip side is that if you can make the connection however you want in the application section, maybe it just makes sense to do it there. Because if you aren't doing this kind of software switching stuff, it probably makes more sense to keep the transmit and RX paths, separate.
I see.
Flow control reasons and whatnot.
Yeah.
But yeah, glad you could join us. So this is the point of these developer meetings is we can mull over some of these ideas and think about ways of building whatever application you have in mind.
Yeah. Thanks for it.
Yeah. No problem. All right. So let's see what's up next. Do the folks at MLE have anything to add about? I know you guys sent a couple of mails around to the list.
Yeah, I just thought we'll start a discussion there, or actually just provide the initial input to everybody, and then we can start elaborating on this whenever it makes sense. And
okay.
Yeah. So
well, I mean, I guess since we're all here, we might as well discuss this briefly at least. You want to give a kind of a high level overview of what it is that you guys are thinking about?
Yeah, so it's basically two kind of separate things. The first is that we also want to implement some logic, traffic analysis and classification logic into the application portion. You already provided us with the API that's currently in place. And we like to add something to this to enable the application to basically select or at least guide the selection of the queues used to deliver the packets to a software program. And I guess that we already talked about this very briefly in another meeting, and that's something that you already were thinking about, but yeah, it just hasn't made it into the code yet. So I guess it makes sense to see which type of interface you want to put in place, and how this should look like, and how flexible it should look like, and so on. So first, we thought about maybe we choose something that is at least a little bit extendable. So provide some metadata path along with the packets, because we think that it must be a per packet thing. And we also want to enable like concatenation or merged usage with the RSS already being in place. So we don't want to replace this, but we also may want to use it in addition to the queue steering present in the API, in the app, because otherwise you would need to re-implement what is present in the RSS module already.
Right. So that's actually something that I've been kind of scratching my head over a little bit, is, you know, the not just the RSS, but also the checksum computation logic for both receive and transmit. You know, where does it make sense to put that? Because it almost seems like to me it would make sense just to re-implement that in the application section if you need it there, because well, so my original thought is you basically go, say, for the transmit path, the data would go from the core data path, which would, you know, DMA it from host memory, and then it would send it to the application section, and then it would go through, you know, like the transmit checksum computation that would then insert the checksum. But what if the application wants to, say, add encapsulation, right? Like wrap the packet in, you know, a GRE or a VXLAN or something, then you kind of need the internal checksum before you wrap it. So I'm almost thinking what might make sense to do is, if you do need that kind of information, just to make another instance of the RSS hash module inside the application section. And then you can compute the hash there, work based off of that. And then, you know, if you modify the packet and change the headers or remove outer encapsulation or something, then, you know, you can compute, you know, an inner hash if you want, you know, as part of the core logic. And maybe what we can do is have it set up such that you can disable the, you know, the RSS computation on the, you know, the main data path if you're already doing that in the application logic. That's kind of what I was thinking, but I'm not dead set on one particular method for implementing that. But yeah, I agree that being able to select a queue in the application section is, at least for RX, is going to be super useful.
Okay, so basically one way to implement this would be to add a parameter to MQNIC core, basically to disable or just remove the RSS portion. Because I guess we don't want to implement it twice, right?
Right.
So really
right,
twice
yeah.
within one bit stream.
Right. Well, I mean, it depends on what you're doing. In some cases, you might need it twice, or at least I was thinking more in
Right.
terms of the checksum computation stuff, and not so much the RSS, but it also applies to RSS, because, you know, for example, if you were getting encapsulated frames that are like VXLAN or something like that, you might want to verify the outer checksum, strip off the encapsulation, potentially do some other stuff, and then hand it off to the core logic, which would then verify the inner checksum. So, you know, having multiple copies of that almost seems like it would be necessary for certain operations. But if you're not making that kind of a modification to the packet, then, you wouldn't need to implement, another copy of the checksum computation logic or something. I'm not sure exactly what makes the most sense there. The other thing I was thinking is that you could set it up so you could kind of recirculate the packet and send it through twice, but then you run into throughput issues.
Yeah, I guess so. Yeah, okay.
I'm not sure I see laying down to check RX checksum computation units as being that big of a problem. I mean, what's the throughput of one of these units? Maybe you need to do this if you have to do 2 checksum verifications. You need to have 2 of them anyways.
Right. Yeah. I mean, that's kind of my thought. It's like we'll keep, a set located with the core data path. And then if you need access to that information in the application section, well, the modules are already there. You just drop down another copy of it.
Yeah,
I guess the other thing is that with the
that's
shared interface.
Okay.
Yeah, the other thing I was going to say is
but-
with the shared interface data path, you only need one per, interface and not one per port. So that's going to help with the footprint a little bit, I think.
Yeah. Well, but with the queue selection, still we need an interface to provide this information, which is not
Right.
available right now. So at least some kind of bypass needs to be present then.
Right. Yeah. So
Yeah.
we need to add something to the receive AXI stream interface, basically, to carry that. And then the question is, are we going to add some non-standard AXI signal, or are we going to jam this into T user? I'm not sure about that. I can see good arguments for both ways. I kind of like keeping it as a separate signal because then it's clear what it is and what it's doing, and you can control its width separately, and you don't have to like pack it into T user at a particular offset and whatnot. But on the flip side, that I don't know how like the Xilinx tools and whatnot handles non-standard stuff. So if somebody wanted to drop a block diagram in here, that might cause problems trying to thread around some additional AXI stream signal. And currently none of my AXI stream models support anything other than the standard signals. So
yeah, and I guess the most worst thing about custom signaling is always handshaking. So there is standard checkers for XC stream interfaces, so you can easily make sure and verify
it wouldn't necessarily
that
be
working.
a non-standard thing to do from that standpoint, right? Because if we wouldn't necessarily stop using AXI stream or something, right? You'd still keep the same interface, you just add a couple extra signals to it. It would just be T something else maybe. But if it's not,
I guess from my perspective there are two ways. One is use T user, the other one is add another XC stream interface, which is just and T data is what we want to transfer,
right?
And it's just used once per packet.
I went down this route with the Verilog Ethernet code base, basically, that uses separate streaming interfaces for all of the headers. And I tried to do this for like the PTP timestamps and whatnot. And it ends up being a complete can of worms when you're trying to keep a one-to-one correspondence between transfers on one interface and packets on another interface. It's easier just to push it into the sideband data and treat it as the same interface. Because I was running into issues where the FIFOs are messing things up when things got reset or things overflowed. I'm like, well, okay, if this FIFO overflows, then I have to drop a packet here, and I also have to drop a cycle of this other interface over there, and it just ends up being a mess. So if this is metadata that's attached to a packet, it should be moved on the same interface.
That totally makes sense.
Now, one thing that we might be able to do is, if you're worried about the size of a FIFO that's storing this, is an idea I've been mulling around is to build a metadata FIFO that peels off the metadata and stores it separately. So you basically have one memory that stores the T data, and then a different memory that stores everything else. And then that'll give you kind of a trade-off between the size of the FIFO in terms of the number of packets it can store and the size of those packets. So you can store potentially the metadata in a little bit more of an efficient manner.
Yeah, and in one project we built such a thing, I guess. Yeah, so everything in this thing operated basically in terms on units of packets.
Right.
And there was an additional something like T user, but on a per packet basis. The problem with T user is you basically don't know if it's per packet or if it's an ongoing thing.
Yeah, that's I mean, I think in the general case, right, that could be a problem, but I think for Corundum, you know, if we're putting all the logic together, we can define it, you know, however we want, basically. So I know for a lot of the other signals, you're supposed to hold it for the entire length of the packet. So we can just say, well, T user is the same for the purposes of
Well,
the interface of the
that's
coordinated
already
graph.
broken at the Mac interface, where it is the end at the last cycle, it's packet valid.
That's true, right? So right, so that's why for, you know, if we're going to do some sort of a metadata FIFO, we'll capture the last cycle of T user and use that for the entire packet.
Right. Yeah. Yeah, I guess that's always tricky with T user. So I guess for the queue handling, we want to have this in the first beat, as we want to steer the whole packet to a specific queue, and not waiting until its end to know where to put it.
Right. Yeah.
So
I mean, most of the other
yeah.
signals work that way, right? Like TID and TDEST are kind of the same idea. Actually, what am I talking about?
Could
We
use
can use
TDEST.
TDEST. Yeah.
Yeah,
To
we
indicate
could.
where it's going. That was going to be my plan anyway, is for the RX and the TX for indicating which port is to use the TID or TDEST. So in the transmit direction, you would put into TDEST. Basically, it would be a combination of the port and the traffic class. And then in the receive direction, it would have the TID indicating the port. But you could very easily use TDEST to indicate the queue that you want to put it in. Now, the flip side, I guess, is how do you indicate, you know, whether to use that value versus to let RSS do its thing? Not sure about that. And I guess another potential consideration is maybe you still want RSS to do something, but maybe you want to restrict it to a certain set of queues or something like that. Like what I was thinking you could do with RSS is that if you wanted to have, we kind of briefly discussed this before, if you wanted to have the driver expose multiple ports as multiple interfaces, what you need to do is subdivide kind of the queue space across all of those sub interfaces, and then you'll have to set up RSS to do. Well, I guess you don't necessarily have to set up RSS, but the idea is that you would set up RSS to spread the traffic out across the queues that are associated with each one of those ports. So you would have to like mask off. We're going to use the upper so many bits to determine which queue we're going to, and then or to determine which interface we're going to, and then the rest of it to determine which queue. So in this case, you don't want to override the entire RSS hash necessarily, but only a few MSBs.
Right. So that was the idea of the interface we thought about. So there was something like a command where we could say that there is a value attached to this command, and how the value is interpreted depends on this command. So we could use basically the command is split up into two sub values, let's say, or the values are split up into two sub values. One is kind of a mask, and the other one is a QID. And if you use both, you could provide like an offset, and with the mask, you could just split off portions of it, which could then be filled by the RSS hashing algorithm. So you define basically the number of bits that's used by the RSS hash, and the other ones are fixed and provided by the app. And this way you could use, yeah, streams.
That's a good idea. So it sounds like you're talking about you would provide two fields, one which is the an RSS mask, and then the other one is an offset. So you take the RSS value, you AND it with the mask, and then you add the offset, and that becomes a QID.
Right. Something like this. Yeah.
You could use tdest very nicely for the QID. I'm not sure about what you would do with the mask. I guess you could put that into user or something, but not sure what makes the most sense there.
Yeah, so that's the thing, yeah, about naming this interface. Yeah, I guess we could also just use tdest for everything, and just there's some algorithm to interpret this, so it's not just straightforward. That's an ID.
Right. Yeah. I mean, you could just concatenate the two together, but then you have some gigantic tdest, which I don't know. I guess it doesn't make that much difference from the standpoint of the logic and whatnot. It's just which signal are we extracting those bits from? Is it in tuser or is it in tdest? And for all of my FIFOs, if that data is stored, basically it concatenates all the sideband signals together and stores it. So it doesn't matter which sideband signal you put it in. It's not like you'd be saving any logic resources or memory resources by putting it in one signal versus another. So
yeah, the only savings would appear if it's per packet interface.
Right, but then that opens up a whole different can of worms
in
terms of keeping stuff in sync. So yeah.
Already discussed this, right?
right. Yeah.
Okay.
I don't know if anybody else has any ideas on this. If this sounds interesting to somebody else, or somebody else has that's totally wrong, you should do something else. Yeah, sure.
Hello everyone. I had a question if you have time and if you don't have any other things left to talk.
Go ahead, fire away.
Okay. Can I share my screen?
All right. Do I need to push the button for that?
Yeah, I think. Yes, you need to push button. I think you need to make me host or something like this. I don't know.
There we go. All right. I think you can do that now.
Oh yeah, I can do this. Where is that? Okay, I will share this.
Got to find the right window.
Okay, I will draw some things here. I have a question about PCI Express. So we have FPGA here, right? And
I'm not seeing your drawing. Are you sharing the wrong desktop?
Okay. Sorry. 1 minute.
I'm just seeing a blank desktop.
Okay. How can
if that
I
helps
do
narrow
that?
things down at all.
1 minute. Sorry. How can I share different screen? So can you disable my screen? I will do one more time. Yes. Okay. Now can you enable again?
I think you. I think I.
Yes. Yeah. Now you can see.
There
right?
we go. There we go. That looks better. Okay.
Now we have our FPGA here, and we have our main memory, CPU, and stuff here.
Right.
We have hard IP here. So we know that there are 4 interfaces here.
Right.
And 1 TX and RX here. So assume that this one is X16 and Gen 3.
Yeah, okay.
3, let me write here. So
it's always fun trying to draw things with a mouse.
Yes, I'm trying to draw with a mouse. And we have throughput limit of about 16 bytes, slightly less than 16 bytes per nanosecond, right?
Right.
Per nanosecond. And if we have 512 bits of interface here, we can send 16 bytes per nanosecond from the interface. Assume that we are not using CC and CQ interfaces. So we are using only, so we are not sending descriptors or anything else here. We are using RQ and RC.
Mhm.
We can send, we cannot send, of course, as much as possible because we have limitations from here and we have limitations from DLLP and stuff, flow control
Right,
packets,
yeah.
right? And what you tried, you have, I think, experience with testing high throughput data transfer from FPGA to CPU and from CPU to FPGA, and can you say what is the efficiency of this in approximately? Not of course we cannot say this
Right.
exactly because there
it's
are
going to be highly
packets,
dependent on the size of the transfers that you're performing.
and do you think straddle option helps us to increase the throughput, or it just makes us hard and low?
It will help by a few
low
percent, but it is dependent on the size of the data that you're sending. And in fact, I think it's actually more important to do that on the Xilinx devices than it is on some other devices. Like, for instance, the Intel P-Tile uses a totally different kind of scheme on the PCIe interface in terms of the streaming, because it transfers the headers as sideband data. And the reason that's important is because the packet payloads for PCIe, the maximum payload size, are all nice, even powers of 2. Well, the bus width is also a nice, even power of 2. So if you're just sending the payload, nice, even powers of 2 on a nice, even power of 2 bus, it all packs nicely. But if you're inserting this stupid header, then it doesn't pack it nicely anymore, right? Because you have, you know, 12 bytes or 16 bytes of header on a 64-byte wide interface, right? You're going to end up with a gap at the end of every frame that you transfer. And one of the things that you get with the straddle interface is you can fill in that gap. So that's actually, at some point, I'm going to be reworking the shim that I have for ultrascale to support straddling and to fill in that gap, because the FPGA independent internal interface that I'm using is basically the same idea as the Intel P-Tile, where they are transferred, where the header is transferred as sideband data. So that basically gives you a wider interface, gives you a little bit more bandwidth for larger frames anyway. If you're trying to transfer small frames, that's a different story. But for small frames, you also have the TLP overheads and whatnot, and you know. So if
Is
you
it
want,
worth
if you want,
the effort?
what?
Do you think it's worth the effort?
It gives you a few extra percent. So
Okay.
the only reason I'm actually gonna bother with that on the Xilinx devices is because I have to do it for the Intel devices. For the Intel H-Tile and the Intel P-Tile, they both use segmented interfaces for RX and for TX in X16 mode. So I have to figure it out for those guys. If I figure it out for those, I might as well use it for the Xilinx devices.
Yes, it would be nice, but it's going to make you harder for you and harder for others to understand the code, because
actually
I think
it's not as big of an issue as I originally thought. So the thing that I like about Xilinx is that you can control the straddling separately on the RQ and the CQ, right? You can turn it on
Yes,
RQ
yes.
and leave it off on CQ, which is really nice. And you can also just turn it off completely, which is really nice. You can't do that on the Intel devices. It's just on and you got to deal with it. So yeah, the other thing is that in the current incarnation of the DMA components, I have peeled off the device specific interface. So the DMA engine that I have that I'm using right now for everything, it doesn't directly connect to the hard IP core, right? It instead speaks this internal TLP interface that I cooked up. That's very similar to the Intel P-Tile interface. And then we have to write a shim that adapts that interface to whatever the hard IP core is looking for. And that means I can run the exact same DMA logic on whatever FPGA you want, which is huge time saver in terms of maintenance overhead and whatnot. But yeah, the idea is that I can perform this kind of adaptation in that shim logic and not in the DMA engine itself. If you want to make a segmented DMA engine, that's going to be a pain. But if you can just adapt in the shim layer and kind of, unwrap or de-stripe that interface, and then have a wider interface going out to your DMA engine, then that ends up being easier to maintain, easier to understand, and then maybe you can get a few additional percent of throughput.
I have one more question. Sorry for making it hard. So in this 512 bits of interface, we have 64 bytes, right?
Yeah.
And if we use 128 bytes of payload, we are going to have two full cycles and one more for 4 double words, right? Because of the header.
Right.
Isn't it better to make it 124 double words to send 120 bytes? I mean, not 24, but 124.
Right. So you get full utilization of that interface.
Yes. Mine's 4 times 4 to 16.
Yeah. Oh, so that's not something I've tried actually. You're not going to be able to get away with that in all cases, I don't think, because I mean, let's think about it like this. If you were going to try to make a large transfer with a bunch of 124 byte frames, eventually you're going to run into a 4K boundary crossing. But I guess it's and then you're going to have to send packets of a different length to work around that, because you can't read or write across a 4K address boundary. But I don't know how that compares to, sending 128 byte frames. I guess you would probably see a savings. I guess the other thing is that maybe if you're not issuing enough operations, or if you're moving relatively small blocks that don't cross 4K boundaries anyway, then maybe that's not a problem. I'm also not sure what the host and other PCI Express components will do with that. Because sending smaller packets, it means you're basically going to be sending more packets, which is going to result in more overhead over PCI Express, right? Because every packet you send that goes over the wire, you don't only have the PCIe TLP header, but there's also some link layer signaling as well. I want to say it's like 8 bytes or something per TLP. And then that also consumes flow control credits, and then for completions, you have a limited number of tags, right? So, well, that's the other thing with completions. You can't really control the size of those that are coming back over the link, right? That's going to be whatever the root complex, decides to do in terms of slicing and dicing stuff. And with those, you really want to be issuing, your 512 byte read requests. So you're issuing fewer TLPs and you're using fewer tags. And then what's coming back is going to be 128, 256, 512 bytes, right? It's not going to be 124 because that's not where the root complex.
It's actually not 124, but 28 minus 16, because this is in terms of bytes.
Sure, yeah.
I made a mistake.
That's fine. Yeah. Okay. So 112.
But you know what I mean.
I know what you meant. Yeah.
Yes. That's...
Yeah. So I mean,
okay.
yeah. So if you're sending stuff to the host, I guess you could do that. It's worth trying, I guess. Well, I don't know if you saw. I have the DMA benchmark program, or the DMA benchmark project. Have you seen that one? I can send you a link to it right now. I'll just pop it in the chat. But you could edit the, it allows you to perform some very simple kind of stride measurements, and just measures the throughput. Let's see here. Do I have a link to this? Yes, there we go. All right, DMA bench. So you can try this with your 112 byte message size or whatever, and see what the performance looks like.
Okay, I will click on this.
We can measure it. Yeah, so that one currently doesn't support straddling. It's the exact same thing as what Corundum is doing. Part of the reason I put that together is so we can experiment with the DMA engine that Corundum uses separately, work out any bugs or whatever before we use it with Corundum, just to make sure that things are operating appropriately. What what FPGA boards are you using? Do you is there a design for your board? I can whip one up.
Oh, we are using a Mango board, VU9P, a Mango board from Silicon. Do you know?
Oh, the silicon.
Silicon.
Oh, okay.
Silicon,
Yeah.
yes.
The Mango, I guess, is
Yes.
their code name.
Yes, Mango. Yes.
Okay. Yeah. Well, I mean, it'll definitely work on that board. It's just I don't have a reference design put together for it. So
We have that board, but I never had chance of testing with 100 gigabit. So I don't have experience with this kind of things.
right. Well, the
We are
DMA
mostly working with HFT these days. So
right. Well, with the DMA benchmark design, it doesn't require any network ports or anything. It's just PCIe. So
okay.
So you should be able to run it on there and get some idea. That basically the way it's set up right now, I've been planning on adding some more capabilities to it at some point. Right now, it basically just runs a bunch of stuff in the driver probe method and then prints it out to demessage what the bandwidth figures are. So you can just tweak the code in the driver a little bit to run the sizes that you're interested in. Eventually.
So this doesn't have interface in the data path, right?
It doesn't have an interface in the data path? What do you mean?
Yes. So you are telling that this DMA benchmark test, it does not have Ethernet interface in data path, right?
Yeah, it's just transferring stuff to and from the host over PCIe.
Then yes, then it doesn't matter. I think it doesn't matter. The card doesn't matter.
It doesn't matter?
Yes, because it has the PCI interface and its constraints are
well, right. Yeah. I mean,
yes.
I think in this case, it probably doesn't make that much difference. Yeah. Well, assuming the board is made with the standard PCI Express, IP core location.
It does have that. It does have that PCI Express hard IP.
Well, some devices use the non-standard pins for that, so you got to go in and change some settings when you generate the core.
So you have.
But it would be very easy to run that design on your board, I think.
15 something board. What was the
1525?
Yes, 1525. I think 1525 have the same things with this.
Yeah,
right?
Probably. And also the Alveo U200.
Yes.
And I think the Alveo U250.
Yes.
All right.
Thank you, Alex. They were my questions. And
yeah, you're welcome to follow up on Slack or whatever with some of this stuff if it would be interesting to see what kind of results you're seeing.
Okay, if I can test this, if I have a chance to test this, I will tell the result. Yeah,
I mean, I think that's kind of the best way to do some of this stuff is to sit down and actually just run a quick test.
Yes,
we can certainly sit down and do a bunch of back of the envelope calculation, but running a quick test that will shed a lot of light on what's going on. So
and I have one problem, a big problem actually. I cannot use this complete Corundum before understanding the all of the parts of this. And for now, I just understood DMA interface write and read, but not completely yet. And it was very difficult to understand DMA interface right part, but when you understand the philosophy of your codes, and it's going to be easier in next part.
Right. Well, I mean, if you have any questions, Slack channel is there. The mailing list is there. Feel free to ask.
Okay, thank you.
Yeah.
Thank you. Thanks, everyone.
All right. So I think well, Ulrich at the MLE, did you have another thing that you wanted to bring up in terms of the traffic shaper that you guys were working on? Or that you guys were thinking about working on?
Yeah, This is Joachim. Hi.
Oh, okay.
I think Ulrich had to leave. So I'll
I
take
still see him
over.
on the list, so I'm scratching my head, but okay. Maybe he'd step out for a minute. Anyway.
Yeah, that's my current guess. I don't know. So, but anyway, so if we still have a few minutes, I think we can go through this other topic.
Yeah, I mean, let me put it this way. I don't have any conflicts. I can keep going if, that's fine with other people. So we're all here. We might as well discuss.
It's fine for me. You can discuss as much as you want. That's beneficial for everyone, I think. If that's not a problem for others.
So I guess not a bad idea to share. So I try
Yeah, I think you
sharing
should be
my
able to do that.
screen here. Share a tab. Get the right one.
Okay, I can see it, but I can't. Oh, did you go on mute? Okay.
I also can't hear you.
Yeah. Let's see here. No. Okay, there we go.
Am I back now?
You're back now.
It disables the microphone as soon as you share something. Oh, okay. That's
Go figure. All right.
Yeah, I guess it's to avoid if there's a tab open in the browser playing something that you have a chance to stop playing it.
Yeah. All right.
Okay,
Anyway.
so everybody sees it now. So this is another part of our effort is to implement a certain traffic shaping algorithm. And for this, first of all, we looked at the current structure and found the scheduler block, which currently by default contains the scheduler RR thing, the round robin scheduler, which already has a controller interface, which is currently not used in the default design, at least on the ZCU 106 board. But we've seen that there are actually the TDMA a scheduler based on PTP. So from this whole existing code, we kind of then thought about, well, how are we now going to implement a different kind of traffic shaping? And we basically came up with the idea to reuse this scheduler control interface instead of, which of course would be an alternative to replace the complete scheduler block altogether. But what we basically need is, which is basically the red part here, a feedback which tells the schedule controller about how much data was essentially requested towards the TX engine. Or to put it in other ways, the round robin scheduler is doing these TX requests to the TX engine, and the TX engine comes back with the status, which includes the length of the payload. And for traffic shaping, we would need exactly that length information to keep track and do our traffic shaping. So we need some interface which transfers this information to a schedule controller, which is, as I said, the red part here in this picture. And what we basically thought is kind of, forwarding the TX request status from the TX engine either through the scheduler RR block or, I mean, in theory, in a separate way, directly to the schedule controller, carrying exactly the information of the length and the associated queue for that matter. I mean, that's what a traffic controller needs, the queue. A second part would be separate from that one, which is the pink one here, is to get even more information from the TX engine, specifically intermediate status updates. We called it intermediate status updates here, because at the moment, if we understand it correctly, the TX request status is coming back from the TX engine if basically everything is said and done for a descriptor, including the completion queue update. So the data is on its way and the completion queue got updated. And what we would like to have in a second step, or not really optional, but it can be a second step, is to have intermediate information, which means, for example, as soon as the descriptor has been fetched, the length which is going to be length of data which is going to be sent out is known. So the question was, why not provide intermediate updates, which in the end tells the schedule controller kind of, this is what's going to happen in terms of length as soon as possible. And
well, I mean, maybe a third option is that we just change the TX request status to respond as soon as the descriptor has been processed.
Right.
That one is really there just to inform the scheduler of, what got sent. But yeah, maybe that could make sense, is to set that up so that response goes out immediately as opposed to after the packet is actually sent.
Yeah, actually, we thought about kind of also as one option, as you said, enhancing the TX request status, and not only telling the length, but also another field which says, well, that's the final information, or everything said and done, and that's now a status update in the middle. So basically carrying another a bunch of bits with which say final status, intermediate status, and so forth. So from that, you seem to prefer to in this, at least in this situation, kind of pipe everything through the round robin scheduler, or is there a special argument advantage of having it not go through the round robin scheduler, instead directly to the schedule controller?
Well, I mean, you could send the transmit request status straight to the TX scheduler controller. Oh, but you're saying that's missing some information, right? That needs to be filled in? Or, I mean, what would be in access desk status that's not in access TX request status?
Right. I mean, we try to have multiple options here. So
Right.
basically in desk status would be the same information.
Well, you're showing it drawn through the round robin scheduler. If it contains the same information, why not just connect the TX request status to both the round robin scheduler and the scheduler controller?
Right. Okay.
I mean, is there a reason that red connection has to be between those two instead of
No.
signal? Okay.
Not at least not in our current way of thinking. No.
Okay. Right. Well, I mean, I think that the proper way to do traffic pacing and whatnot is actually to implement a weighted fair queuing type scheduler instead of a round robin scheduler. Is that something you guys have thought about, or?
We basically thought about replacing everything, the whole scheduler block.
Right.
But then we thought, well, actually, it might make sense to have the round robin scheduler still in place. The basic argument was, well, what about assigning a certain data stream to a number of queues, which shall get serviced, in a round robin fashion.
So I mean, the concern with that is that if you assign the same stream to multiple queues, you're most likely going to run into issues with reordering. I mean, I guess it's not guaranteed that you're going to run into reordering, but you could run into issues with reordering. And that may be a problem for whatever it is that you're trying to do. If you keep everything on the same queue, then you're not going to have any problem with reordering for that particular flow.
Right, yeah. That's of course correct, yes.
And just FYI, I may be in some of the changes for the shared interface data path and whatnot, there may be some loosening of the ordering components, right? The ordering restrictions, because I know for a particular queue, things need to be kept in the same order, but for different queues or for different ports or whatever, then the ordering does not need to be preserved. So I'm not sure if it's just going to be, I'm not sure how much looser it's going to get, but as a general thing to keep in mind, don't rely on the ordering being preserved between different queues, because the assumption is that those packets are part of different flows and that there's going to be no issues with ordering.
Yeah, I mean, from a software perspective, I think the Linux networking stack at least is I'm not 100% sure, but I think it is the following way. It makes sure that stuff which shall not get reordered is put into the same queue.
Right. Well, you were talking about, taking a flow and distributing it across multiple queues, which seems like it would violate that.
Yeah, then I guess my kind of way of saying it was wrong. It is basically the assumption of having a kind of a virtual device in software, which then would have, say, 4 queues, which in the end make it to a subset of 4 queues of the Corundum NIC, and then would get serviced, basically like it's now with round robin. And on the other hand, software is making sure that stuff which shall not be reordered is simply put into the same queue. That was my thinking.
Right, but it sounded like you wanted to use different numbers of queues to generate different rates. Or I guess maybe I misunderstood what you were trying to say.
Right. Basically, a certain data stream may be comprised of multiple or go to multiple queues. in terms of how it's done in specifically in Linux, shall get associated with a certain amount of bandwidth. Yes.
Well, so you guys, for your traffic shaper, you're basically trying to impose bandwidth limits on a per queue basis.
For starters, yes, on a per queue basis, but it is yeah, kind of in the future we might need to go to the situation where a data stream is not one single queue, but it's actually mapped to multiple queues.
Mapped to multiple
So
queues, so it's not one data stream, or
yeah, sorry, my again wrong wording. If I say one data stream, I'm thinking of one data source in terms of Linux.
okay,
And
okay, I see.
the kernel is then depending on
Right. So one data source could be providing multiple streams, and then those streams could end up on different queues depending on what Linux does. Right.
Right.
Okay.
But a certain subset of queues.
And you want to limit the source, not each individual connection, basically.
Right. That's the way we can put it. Yes. Mm-hmm.
Could you use the Linux TC module to kind of override the way the kernel usually assigns queues to send everything from that source to a single queue?
Sure, but I mean, if we are at this point in time in the future where we need to do that, the whole point of it is to actually would be to have multiple hardware queues. That's the whole point.
Right. Yeah.
So I mean, obviously the first step would be just to have one data source mapped to one queue, of course. First step.
Right, yeah.
Which is then simple because, well, the bandwidth association is just with one queue.
Right, because if you're going to rate limit anything, you need to make sure that you can associate the flow with the actual hardware resources that are going to be doing the rate limiting, right? So
yes,
one-to-one, that makes things super simple. If you're allowing the operating system to pick whatever queue it wants, then it's not clear how you're going to rate limit anything.
Yeah, and that's why we thought about keeping the round robin scheduler. So the schedule controller would kind of limit the traffic for the data source and instruct the round robin scheduler. Well, now you can schedule a subset of queues, multiple queues.
Okay, so how would you know what data source it's associated with then? If the OS can put it in any queue, are we talking about you're actually going to have a module that's looking at the contents of the packet?
We would make sure that a certain subset of queues is uniquely identified with a certain data source. Yes.
Okay. All right. So, okay, a certain subset of queues. Okay, so not necessarily.
Yeah, in the second step, talking about the second step, in the first step with a single queue.
Okay. Okay, so eventually what you want to be able to do is enforce a rate across multiple queues. It sounds like kind of in aggregate. Yeah. Okay. So you want to build not just a rate limiter, but like a hierarchical rate limiter.
Yeah. Okay. Yes.
Does that make sense?
I think so. Yes.
I mean, I guess is that a term that rings any bells or not so much?
Yeah, it rings a bell from having used Linux TC with the HDB queuing discipline. But yeah. I have to think about it. If it's really the same or not.
Well, I'm trying to figure out what exactly it is that you guys want to implement, ultimately.
Well, ultimately, it's about limiting a data source in its amount of bandwidth.
Right. And
with the
you
first
wanna do
step
that
of having
through packet pacing ultimately. So you're inserting delays basically. If it tries to send faster, then you're gonna, make it wait.
yeah.
Right. Okay. Right. So you're talking about first pass, you're going to try using the transmit scheduler controller to control the existing round robin scheduler instead of writing, a weighted fair queuing type scheduler, which can directly enforce rate limits on a per queue basis.
Yeah, I mean, we currently basically see it the way that the round robin scheduler would help in this future scenario, which might be a wrong assumption, of course.
Well, so a weighted fair queuing scheduler, you can always implement a round robin schedule on one of those, as far as my understanding anyway.
Mm-hmm.
Because if you just assign all the weights to one or the same, then you basically get a round robin schedule.
Right. Mm-hmm.
But then if you set the weights to something other than all the same, then you can, enforce, different rates for different traffic.
Right. Mm-hmm.
So the more general solution would be to implement, a more powerful scheduler instead of trying to, shoehorn the round robin scheduler into doing something it's not really, designed for, if you know what I mean.
Yeah. Mm-hmm.
Have you guys looked at all into how you might build a more complicated scheduler, like a round, not a round robin, but like a weighted fair queuing scheduler? This is something I've looked into in the past, and I have looked up a few papers. I can certainly dig those up and send you some links.
Yeah. Links are always welcome. Yeah, we looked at several things and kind of have narrowed down on a certain one. But well, as I said, input is always welcome, as usual.
Well, you said you've narrowed it down to a particular one. So like, you mean this scheme that you're talking about here, or something else?
Yeah, I guess the problem for me is now to explain why we think that having the round robin scheduler still in there is not a problem. I mean, if perhaps if we go back, what if our understanding is correct? I mean, that's also one thing we are trying to clear up here.
Right.
If we understand correctly, the schedule controller is basically commanding the round robin scheduler and says you can queue this particular queue if it has data, and you can not queue this other particular queue at any point in time. And so the round robin scheduler looks the queue up or gets a doorbell if there's data available. Okay, and we have the grant to schedule that queue. Then the round robin scheduler will take that into its FIFO and do round robin schedule with the granted queues.
Right. Okay, so your idea is to, pause and unpause the queues basically to try and enforce a specific rate.
Right. Yes. Mm-hmm.
I mean, I guess that would probably work. It sounds like it might not be particularly reactive. I don't know. Let's think about that. It sounds like you would basically have to end up implementing a, weighted fair queuing kind of scheme inside of the transmit scheduler controller in order to actually enforce that. And that if you went to that much trouble, you might as well just implement the weighted fair queuing directly.
Yeah. Mm-hmm.
So one thing to keep in mind with Corundum is that, I'm only one guy, so I had to simplify stuff as much as possible when building stuff originally. So my goal is at some point to implement a more comprehensive scheduler, such as, weighted fair queuing, which would be able to implement rate limiting and stuff like that. I only implemented a round robin one because I needed some sort of scheduler to get things running. And then with the intent of revisiting the scheduler later and replacing it with something that was going to be much more powerful, much more comprehensive. But exactly what that needs to look like, I'm not sure. So I think the proper solution for doing rate limits is to implement, a weighted fair queuing type scheduler. And there's a couple of different methods you can use to make a weighted fair queuing scheduler implement rate limiting, and a bunch of different papers that I've looked at previously that discuss various aspects of that. And then I think there's other stuff you can do with weighted fair queuing anyway. If you want to, I guess the other thing is if you do it right, it doesn't just implement rate limiting, but it also degrades nicely into proportional fair sharing based on the rate limits that you have selected. And it just does all this naturally based on how the scheduler works. I'm not sure if it would be more or less complicated to, try to build a new scheduler versus to try to build a scheduler controller that can make an attempt to enforce rate limits. But I think it's definitely something that's going to require a little bit more thought. You haven't really mentioned much about what kind of alternatives that you've looked into. I mean, it sounds like you're going this route just because the round robin scheduler is already there, and it seems like you're thinking it's going to be easier to write a scheduler controller than to write a more powerful scheduler. Is that an accurate assessment, or have you guys not really been?
Yeah, I think so. Yes. What would be one way to say it? Of course.
I mean, it's a different story if you really need that round robin scheduler for some reason. You've drawn up a scheme here, and I'm just trying to get my head wrapped around, is there, what the intent is behind this particular design.
Yeah. So the whole idea of keeping the round robin scheduler is to, in the end, if there's one data source which basically occupies multiple queues in the end, then what we would like to have is to do traffic shaping, associate certain characteristics with this set of queues. And so the idea was, well, the set of queues, the queues which are within one set shall be treated equally, meaning round robin, or at least it doesn't sound wrong. So you put it in other words and said a kind of hierarchical thing of having first a dedicated traffic shaping for the data source, and kind of the second layer, a round robin thing, which then deals with equally sharing among the set of queues. The set of queues which are enabled or disabled, or granted or not granted, based on the let's call it the outer traffic shaping. That was the thinking of keeping this, or arriving at this structure.
I see. Okay, so you want to have multiple queues that are associated with the same data source. You want to kind of put all of those queues into one bucket, right, to control the rate across that group.
Right.
But then you want to fair share, round robin those individual queues in that group. You want to make sure that they all get to send at at their piece of the rate.
Yeah.
Well, we have Brent Stevens on the call. Brent, you guys, I think, know a lot more about scheduling than I do. Do you have anything that you want to add to this?
Yeah. I think a few things, first I'll echo what you said. If you're doing rate limiting, that's not what a round robin scheduler is for. You should build a separate rate limiting module in front of whatever you're doing. This reminds me a lot of this paper, Scenic Scalable End Host Rate Limiting from NSDI. I'll drop a link to it in chat really quick. NSDI 14. I don't think they actually have an FPGA implementation, but they sort of sketch a design that I think I would say would be very helpful if you're trying to implement rate limiting on the NIC. But so let's say as a first straw man, something with just token buckets where packets from a given traffic class. That's the thing. So I actually disagree about this being hierarchical. This isn't hierarchical because you are not applying rate limits to the individual flows. I suppose it's hierarchical in that you have a fair sharing policy over a rate limit. But importantly, like you have a fair sharing policy. You first have this, round robin policy above your rate limit. And if you're trying to build this, I think the way you are, it's like you're trying to. I'm not sure that there's there might be a mismatch between where or the order you're trying to implement these things in. I think as a final comment though, be prepared to buffer a lot of packets on your NIC if you're implementing this right before the TX engine. I mean, if you're implementing this right before the Mac, which is where it seems to be. I think
where would you be buffering the packets here? Because if you're doing the rate limiting in the scheduler, then
is this before DMA? I thought this was after DMA.
The scheduler determines what is going to get DMA'd in the first place.
Oh, okay. Well, I didn't understand that, so that doesn't seem to be a problem here. So that's good. I think the big thing here is you should have PIFOs are a thing that allow you to build programmable scheduling. If you don't care about programmable scheduling, what you should just do instead is, a hard code, a pipeline of your policy. And so you have, a round robin policy possibly across, multiple queues. And then all of these accesses are rate limited. And so I'd say just build another round robin scheduler somewhere and put in a token bucket rate limiter in the appropriate place, before or after that. And so.
Okay.
But I think you should, if you're rate limiting has, been something you've been talking about, I really think the answer is build a token bucket somewhere. Right. I mean, round robin isn't for rate limiting. In your system, once your rate limit is that your token bucket, once if there's a token in it, you then, go to your round robin across your queues.
Right. I mean, that would basically kind of also happen here. I mean, the schedule controller would say, well, there's a bucket, there's a token in the bucket for a certain queue. let's tell the scheduler round robin here, the second stage, to allow it to actually dequeue something from that particular queue.
Yeah, I think you can formulate it in a number of ways, but I'd say, token bucket's the thing that was missing from this discussion.
Yeah, I need to refresh my memory on token buckets. What's the difference between like a token bucket implementation and like a weighted fair queuing implementation?
Oh yeah, I mean, they're very different. One's work conserving, one's non-work conserving to start with. So weighted fair queuing is implemented with virtual time. And so
it
every
seems like
time
you don't have to implement with virtual time, right? You could set that up so that it's rate limiting, or
weighted
so
fair
it's working
queuing is
based
not
on
rate
wall clock
limiting.
time, basically. But
I mean,
I think there's several variations of weighted fair queuing.
well, I don't really think. What do you mean by doing weighted fair queuing with wall clock time?
I mean, weighted fair queuing with virtual time, the idea is that you will advance the virtual time to whatever the next element is in the queue. But it seems like what you could do is that you could actually try to enforce some actual idea of time so that you actually have rate limits that are, defined based on, wall clock time or whatever, instead of just taking some slice of the pie based on.
I'd
weight.
really recommend you read the PIFO paper. And I think the
Okay.
big thing that's missing here is.
Do you have a link to the PIFO paper?
I guess I can find one.
Okay, I'll see if I can locate that.
I found it. And so you're correct. Just I would very much disagree with you using the term virtual time here. And if we use the word, maybe a more general word like rank, you are correct. And this is what PIFOs do. You can perform, if you have a priority queue, you can use this priority queue with virtual time to implement weighted fair queuing. If you have a priority queue, you can also use your rank as actual time, and now you have a rate limiter.
Right.
And I think that's what you're saying. And that is very much the insight of the PIFO paper. But I think one of the things that they do in their implementation is they actually have, at any given point in time, two separate queues. One that is their work conserving scheduler, and one that is their wall clock rate limiting scheduler.
Okay.
And this is actually a bit dumb, and I go into this in my paper Loom. You shouldn't have end queues for wall clock scheduling because wall clock time is wall clock time. Just use one queue for wall clock scheduling.
Well, I mean, hey, this is the opportunity to sit down and figure out what is going to be, a pretty flexible implementation for a
so
transmit scheduler
in the open
and then implement
source,
it.
So in the open source code that we have for Panic, we took someone else's open source, implementation of PIFO. Jetchen actually, I think, improved it a little bit. And so, maybe even that's the other suggestion. If you're rolling it yourself, just roll some sort of custom hierarchical token bucket round robin, connect them in the right order.
Right. I mean, I guess there's a difference between, building something that's going to work for, these guys' application versus building something that would be appropriate as a general scheduler for Corundum, right?
So the general scheduler is, state of the art these days is PIFO. And there's maybe PyEO, but that's sort of just an optimization that improves scalability at the cost of increasing latency by making it hierarchical. But so really, ignoring that, I would say, if you're wanting to build the general thing, it's take someone else's PIFO code and just put it here.
So you said you implemented this in your Loom thing?
Was that Panic?
Panic, and that was running on an FPGA.
Yeah, it was on the alpha data.
And what kind of
this is in Corundum?
How scalable
we used
was
Corundum
the
for this? So
yeah, how scalable was the queue implementation the PIFO implementation? Like how many entries
I
could you
think
store in there?
I'm gonna defer to Jiachin on this. You can ping her on the Slack. She's active on there. I don't recall. It might be in the paper. It was Jiachin who actually implemented it. I haven't
Okay,
compiled a line of Verilog in years. I'd
All right,
like
all
to
right.
start doing that, but I haven't. So
I mean, I would just just trying to figure out order of magnitude, right? Can you fit 10 entries in there, or can you fit 10,000 entries in there? I mean, there's
I think it was on the order of 100 to 1,000.
okay, all right.
I think part of the problem gets to be you need multiple of these to build hierarchical policies. And I think we just put one in.
Right.
It's yeah, I think we can maybe pick this up after people had more time to look at it, but I'd say
Right.
looking at
Yeah.
whatever is in the Panic open source repository is a PIFO scheduler that's wired up in some way to work on Corundum. It's wired up in not where you would want it, because we were doing this for on chip packet scheduling,
Right.
not DMA packet scheduling.
Well, I mean, if it runs, then maybe it can be adapted. It's
Yeah.
if it's on the FPGA, then it's potentially a block that's available for use in other ways. So
Yeah, exactly. And so I mean, I think it should be modular. Did that answer your question? Or do you have any more comments or,
well,
or questions on that?
that's some pretty good insight there, because I know you
I
guys
guess I was
have
trying
done a
to
lot with more with these
Jiao
schedulers,
Chim,
but,
or who
oh
was the
yeah,
person I was talking? Was
Joachim,
asking that?
yeah.
Yeah,
Joachim,
valuable
right?
information. Valuable information. Thanks a lot.
Yeah, I mean, so if you can't find the open source repository for Panic, let me know. It's linked to in the paper.
No, we have that.
Okay.
Okay. Well, that's
Yeah,
good.
thanks a lot for the feedback. So perhaps to come back to the question at the beginning regarding this potential new interface here from the TX engine, Alex, from your point of view, there's at least at this point in time, at this moment, nothing which where you say no, that's a bad idea to have such a feedback interface there.
Oh, I think it's a good idea. I mean, yeah, I would like to absolutely support being able to do rate limiting and whatnot in the scheduler. And if we need to make some tweaks for that to work, then, let's do it. And I guess the other thing is, in terms of the request status that gets handed back, it potentially makes sense to have multiple interfaces. On the flip side, having a single interface is a little bit easier to deal with on the scheduler side. So I think there's potentially a couple different directions that we could take this in. So one of them is to add another status port. Another one maybe is just to modify the way the current status works, because like I said, right now you get that response after the packet is totally made its way out onto the wire. But there is a question, from the scheduler's point of view, is that really the right feedback mechanism? Maybe it makes sense to try to get that feedback to the scheduler as soon as possible, as opposed to down the road, once the packet has actually hit the wire, because that'll allow you to send packets more more quickly, right? If you have, say, let's say you built a round robin scheduler, not a round robin. Let's say you built a weighted fair queuing type scheduler. You would need to know how big that packet was that you sent in order to reschedule that queue to send another packet in order to get the
right
rate. And if you're waiting until the packet actually hits the wire before you get that response, then that doesn't end up being very useful. So since this interface is basically present for the scheduler, if it makes sense to change this to return its response immediately as opposed to later, then that's definitely something that we could consider changing. I mean, I think right now it's not even really being used by the current round robin scheduler, aside from, was the queue empty or not? Because if the queue is empty, then, you deschedule it. But if the queue isn't empty, then you can reschedule it. And I think the way the round robin scheduler works is it just assumes that the queue is still has data in it until it hears otherwise. That's the only way you can get anywhere near line rate with round robin, which works for round robin. But for other schemes, you might need a slightly different approach. Oh, I see Ulrich has joined us again.
Yeah, of course. So, but just to make sure that we're on the same page, this is what our intermediate status updates here is all about. To perhaps not only make the TX engine report as soon as everything is said and done regarding a descriptor, but also have intermediate status updates, so that as soon as the descriptor is fetched and the length field is kind of there, then provide feedback right away at that point in time, while fetching the data or whatever.
Right. Yeah. I mean, that's kind of what I was. Okay. So you're saying keep the status the way it is right now, but add an additional output that can be considered.
Yeah, that's sure. That's for sure one thing here. I mean, we named it here differently, but of course it can also be part of the TX request status.
Right. No. So my point is, I think that's a really good idea, but I'm just trying to figure out, does it make sense to report, the transmit request status all the way at the end once the packet has actually hit the wire? Does that serve any purpose, or should we just convert that to, this intermediate request, right? So as soon as the descriptor has been read and the transmit engine knows how big the packet is, maybe we just inform the scheduler saying, hey, we just sent a packet, that's the size.
On the other hand, I think there's some state associated with a TX request. I mean, it gets a tag between the scheduler and the TX engine, and as soon as the packet is done, completion queue is updated, then the queue the state is freed up in the TX engine regarding that tag. So I think a feedback at the end also needs to be there.
All right. Yeah, I think the other thing too is that right now the way that status is returned, it's a little bit screwy, because basically it can be generated from two different points in the transmit engine, right? It's either generated as soon as the descriptor is, comes back, because that's going to indicate whether the queue is empty or not. And if the queue is empty, then it just returns the response immediately, versus
end of file.
Right. Yeah. So I guess if you provide that on two separate interfaces, then that might simplify things a little bit, because then you don't then the transmit engine doesn't need to merge those, because they're coming from two different sources. And then it's just a question of, what you need to look at in terms of the scheduler. You could just ignore the the response at the end of packet if you don't care about that.
Yeah, I mean, in this modular design, I would say in any case, a scheduler block, no matter how it looks like, I mean, it can take information or ignore it. The point is, a certain block needs the information, a certain other block does not need it. Yeah,
I can definitely see the argument for adding that at that point, to inform the scheduler, as soon as possible when, the packet is being sent. And then, sure, we can keep the transmit request status the way it is now in terms of reporting the end of the operation. So no, that piece makes a lot of sense. That we should definitely make that happen. But the other component is just in terms of the scheduler itself. It would be nice to implement a more flexible scheduler module in Corundum that can be used for other purposes. which is why I'm kind of leaning towards, maybe we need to implement, some sort of weighted fair queuing or PIFO type implementation. But, I guess it's also up to you guys as to what you want to implement and what's going to be most appropriate for your application. Because obviously implementing some sort of a PIFO type thing could end up being a lot more complicated. But the flip side, I don't know what's going to go into your scheduler controller. If you have to implement, PIFO inside of your scheduler controller, well, maybe you just should make that the scheduler.
Yeah.
Because like Brent was saying that, the using a round robin FIFO for rate limiting is not the greatest solution, because what could happen is that you allow the transmit scheduler to send a packet. And I mean, the way it's set up right now, you're either turning the queue on or you're turning it off. You're not saying I'm allowing you to send one packet. Now, if you turn it on, it could send 10 packets before you can turn it off. And that might not be what you want in terms of your rate limit, right? Kind of the idea, I think, is to not have bursts of data going out the door. But
yeah, sure. But there's the important point. As soon as there's early feedback, you can also close the door early. That was the idea.
Right. But the thing is, the round robin scheduler could just be sending packets back to back. It could send, 20, 30, 40 packets or something before you get that feedback back, right? Because even if it's early feedback, it might have to do a round trip over PCIe DMA to read the descriptor, right? And that could take a while. And during that time, the round robin scheduler could queue up, a whole pile of packets to send. And then they're going out the door, whether you pause the queue again or not. Right?
Yeah, okay.
Right, because think about it this way: if the transmit engine is idle and you have a queue that you want to send at 10 megabits a second, so the transmit scheduler controller unpauses it, the round robin scheduler is just going to start issuing transmit requests for that queue, right? And if the next descriptor is not in the cache in the descriptor management module, then the transmit engine will issue a request for the descriptor, but that has to go out over PCIe, which might have a microsecond of latency. So you get the response a microsecond later, even though it's the early response. It's a microsecond later, at which tells the transmit scheduler controller to stop sending. But at that point, you've already queued up 20 packets to send. So you can see how that's a problem in terms of enforcing a rate. Versus if you're actually doing the rate limiting in the transmit scheduler, then it can go, okay, I'm going to send one packet. We'll see how big it is, and then I'll schedule another one. Well, it hasn't gotten a response, so it doesn't know how big that packet is, so it has to wait until that descriptor fetch takes place, and it knows how big the packet is, and it's okay, so that packet was this size, and let's go ahead and update our internal state, and we can schedule a few more since it took so long to read the descriptor.
Yeah. Yeah, on the other hand, any waiting is, well, it's also a question. I mean,
well, so
waiting shouldn't happen in terms of that one queue blocks everything.
Right. So in this case, the way all of the stuff is set up is so if you're waiting on one queue, it can still service other queues, right? It just won't reschedule that queue until it knows how big the packet is.
Yeah.
If that makes sense.
Yeah.
Because
I think so, yes.
this is a common way of building the PIFO type schedulers is you just use a gigantic priority queue, and whatever bubbles up to the top of the priority queue, that's the packet that you send, right? Or that's the queue that you send from. And then once you send it, then you recompute what the priority is, basically the next time you're going to send from that queue, and you stick it back in the queue, right? And then it'll bubble up again, and then when it pops up at the top, then you send it, right? So if you want to do so. The way you would set something like that up in Corundum is that you wouldn't put it back in the queue until you know how big the packet is. But you can still pull more stuff out of the queue and process it, right? In the meantime, until you're waiting for that response to come back. So that's kind of all of I kind of liken it to juggling, right? You need to keep a bunch of balls in the air at the same time in order to be able to saturate the link rate and deal with all these packets. That's especially a problem for the DMA, but it's also a problem for all the schedulers and whatnot. So you have to have, you know, tags to keep track of stuff that's, you know, in the pipeline that's being processed. So yeah, that's definitely something that you have to take into consideration with building the scheduler, specifically so that you can deal with, you know, not knowing immediately what the result is.
Yeah.
All right.
Yeah, I think we will think about it with all the input. Thanks a lot.
Yeah, and if you guys have, I mean, I haven't heard anything from you guys in the past 2 weeks on any of this stuff. So, you know, if you guys are having internal discussions, I mean, feel free to include me because I might have some resources or whatever. Like, I think a lot of the papers that Brent pulled up here are also papers that I would have been able to forward you guys. But I don't know, maybe you guys have found some of these papers too. So if we can keep a tight loop, then, you know, we don't have to save everything for the developer meeting, you know.
Yeah. Yeah, okay. Yeah, again, thanks a lot. Also, Brent, thanks a lot for all the information.
It looks like he had to go, but anyway.
Yeah, and so I guess we will, come up with a first implementation of such an interface in the described way.
All right.
Okay.
I mean, it sounds like that should be a pretty simple modification of what's going on in the TX engine right now, but yeah.
Yeah. Looks, that's our assessment, current assessment, yes.
Yeah. Oh, have you guys done anything with the Stratix 10 devices, or I guess you guys are kind of on hold until you get hardware?
Since Uli is back, I don't know if he wants to say something on this. What I can say is that
yeah, so so what we are currently doing is we are doing the planning for our Stratix 10 based card. So power estimation,
right, because you guys are going to be making your own
so
hardware
on
for that. Yeah.
Right.
Okay.
So that's what we are currently doing. So we are basing this on top of your commits, and I guess that works out fine for us right now. Well, all of us know that we have to do some work on at least at some point closing timing, and we also have to look at resource consumption. So for our device, we are out of block RAMs. So we will,
you guys
have a look
really
at
small
this
device,
one.
I guess.
Yes. But so we will have a look at this and see where we can optimize a bit, and we haven't looked at it yet. So we may have another discussion about this one. We'll see. I think you expanded the text space, for example, and maybe we will just shrink it again. Such
that
things
should
I guess.
not have a huge impact on block RAM utilization, I don't think.
Possibly not, yes. So we will first have a look at where the
but it's a
block RAM
parameter. You
resources
change
are
it, you see what
located.
happens.
Right.
How long did it take to build? 2 hours?
No, it was quickly actually. I don't know, but for me it was about definitely less than an hour.
Well, you guys are you synthesized it for this for your device, right? The
right.
Okay.
Well, the Stratix 1040.
It takes a longer time, I guess, for the bigger parts, even though it's the same number of resources. Yeah. Anyway.
Yeah, possibly correct. Yeah, and maybe I was using one of our faster machines for this. I don't know. Yeah. Okay. Yeah. So that's what we are currently into. So we need to finalize pin outs and to kick off the PCB production and so on. So
are there pin compatible larger parts just in case
yes,
it ends
there
up not
are.
being okay? That's good.
Yeah, that's good. However, getting parts is not so easy. So
well,
we are almost
that's a different story. I mean, I guess sure you can get the FPGAs from Intel, but it's everything else now, right?
Yeah, kind of really everything else. It's clock generators, power supplies, all of this is short.
Well, I know that Intel makes the Empyrean or whatever regulators.
Yeah, but
try
they
to push
set
those,
that
but
end of life just now.
Really?
So there is
Okay.
last time by sometime
Wow.
next
So what, that
Q1
entire
or
line
something?
is coming to an end, or what?
Yes,
Wow. Okay. Interesting.
all the Empyrean or what is called power supplies are end of life now.
Hey, this is why people avoid Intel parts, you know. They just scuttle the entire line. It's like they're
Yeah,
wondering why their
so-
IoT solutions never took off. Well, they pulled the plug, and now, well, they just confirmed why nobody uses them. Oh man.
Yeah,
Okay.
so that's a bit tricky now. And it's really the Stratix 10 power supply is interesting, as they, at least for various devices, use an active power tracking or voltage tracking, as they do within the CPUs as well.
Yeah, I was trying to figure that out. I noticed stuff in the configuration files for power management.
Right.
Like, what the heck is going on there? But yeah, I guess that makes sense. Yeah, they're talking to the regulators, and so
Yeah,
you
so
can't just
they
put whatever regulator you want. You need to get one that the FPGA can talk to.
Exactly. So at least for core voltage, that's exactly the case. They have a little processor, triplified processor core, something like, you can think of it as a merger of the CSU and PMU within the Xilinx Sync ultra-scale
It's the
bus
SDM,
devices.
right?
Yes, that's
Yeah.
called the SDM. And this one first
bunch of
fetches
stuff.
its firmware and then configures the FPGA, and afterwards it transitions into controlling power, and it also does the bit stream encryption or decryption in this case.
The SDM is a secure device manager. So, you know, anytime you're doing any kind of configuration related stuff, you got to go through that. So just to make things more interesting, you know.
Exactly. Yeah, this is really yeah, a bit more complex than it has been in the past. Yeah, but I guess from a configuration perspective, that doesn't matter that much. But from a power perspective, this really yeah, it doesn't help, and especially in the situation where you can't buy any power supply you want. Actually, most of them you can't buy. So yeah, you're really up to what's left over, basically.
Well, I guess you just have to make sure whatever you end up using, you buy all the ones you need before you order the board.
Exactly. Yes. So that's,
you don't design it in unless you have stock in hand.
Right. That's exactly how people do it right now. So, and even so, if they do it differently, the people we are doing the board with, they said that they had their top power supply redesign was 5 times for one PCB until first production.
Wow.
So this is really
bad.
Then. That's a lot of overhead to do.
You know, I'm almost wondering if in the current conditions, it makes sense to do like a daughter board for the power supplies. And that way you don't have to respin the whole dang board if you can't get a regulator.
Yeah, I guess the PLDA people did this with a couple of PCI Express cards they built. I don't know. So I'm not so convinced with power supply daughter boards, especially for PCI Express cards. You don't have the height available. So
yeah, that's true.
You need compact sizes, and there's a lot of power going through these pins, right? So even
I mean, I'm not saying for everything, but for, you know, some of the regulators, and you can always do like castellations and things like that and just put it right on top of the board. I don't know. It just seems like that could end up being a way to, you know, hedge your bets a little bit in terms of component availability.
Yeah.
Like you put the core supply on the board, fine, but for the transceiver supplies and for the, you know, if you have DRAM or whatever, it would suck to have to redesign your board because you couldn't get a regulator for the DRAM termination voltage or something.
Yeah, it could happen.
Yeah.
Right. Yeah, but that's our current task. We are more focused on and doing some other, let's say, research or testing before actually going to production with stuff.
Right.
So once this is pushed out of the way, we can resume on doing our FPGA internals.
Right.
Yeah. Because
Well,
then
and I guess
production
you
has
heard-
its own way.
Yeah. I guess you heard previously that I also have most of the simulation framework updates more or less
Yeah.
squared away for Zinc support. So hopefully
Yeah, that's
we'll
great.
be able to sort out whatever weirdness you were seeing is like a bug in the DMA AXI interface modules. So hopefully they'll turn up in simulation. We can fix it. So you guys aren't doing
Yeah.
burn and churn, but we'll see. I mean, I guess
Yeah.
even if you do have to do burn and churn, being able to test the design every time you make a modification is still a very useful thing to be able to do. So anyway.
Yeah. So yeah, we will revisit this. We are currently also working on the 1 gigabit interfaces and so on. So I guess we will also provide some pull requests for this soon.
All right.
Or some issues. I think that
well, I mean, feel free to contact me on Slack or via email or whatever if you have any questions about anything. So
yeah, I guess no, it's working fine on the ZCU 106. And I guess we will just provide an update for the design because there are people asking for 1 gigabit support, right?
yeah, I think there were a couple of people asking about that. But yeah, I guess that there is a question of exactly, how you go about implementing that in terms of, well, I think for gigabit support, there's probably not that much that needs to change. I think the main things that maybe need to be touched are the like checksum computation modules, possibly, and maybe RSS. Other than that, I think everything should just work. There was somebody asking about like running it with a narrower PCIe interface, and that's a slightly different story.
Yeah, right. Okay.
All right. I think that
Joachim,
about rounds out everything that we need to discuss, right? So
I don't know, maybe Joachim wanted to come up with an item.
It just came to my mind again. I think I didn't even mention it last time. I'm not sure, Alex, are you aware of that we replied to one of the GitHub issue items?
oh yeah, I saw that. Yeah.
Okay. Mm-hmm. So in the meantime, we pushed our sync MP porting effort to our MLE GitHub account.
Right. Yeah, I saw that. I haven't taken
Okay.
a super close look at it. I did notice that it looks like you pulled in a bunch of additional kind of build related stuff. So I don't know, was that stuff you guys have developed internally or? Like
That's right.
files and
You're
stuff? Okay.
referring to our so-called PS make.
Yeah, I think that's what it was.
It's
Yeah.
yeah, it's a lightweight wrapper around Peda Linux, basically.
Okay.
To build these Linux-based boot files
Right.
for the sync devices.
Okay, so
Yeah,
that one is kind of your work in progress at this point, right? You said you were running into a few issues with that, so hopefully once
Yeah, that's
making the framework operational, then
exactly
we can circle back around to that.
yeah, that's exactly our current state, which shows the described unfortunate behavior.
All right, well, we'll get to the bottom of that one way or another. All right.
Sure.
All right, so I guess if that's everything that we have to talk about, then I guess I'll go ahead and close down the meeting for now, and we'll reconvene in 2 weeks, right?
Yes,
Okay,
Sounds good.
sounds good.
let's do so.
Talk to you.
Yeah.
Have a good day.
Have a good 2 weeks.
Will do. Same to you.
Okay.
Same to you.
Thank you.
Thanks. Bye.
Bye.